morning, everyone. And once again, thanks, Kate Yetman and her father, calculus teacher Chris Yetman, for the wonderful rendition of our theme song that we're going to use here over the next few weeks, probably. The song's starting to grow on me. Brian and I had a conversation about that. So again, thanks to the both of you. Welcome to our second Friday here with our AP Live, AP Calculus BC edition. We're going to be talking about, obviously, working with geometric series today, which is another pretty simple test that will probably allow us to solve some problems that don't take a whole lot of time and effort, and just a few steps to kind of get the conditions of this test squared away and whatnot. We have once again several documents that you all have access to. So as always, you can find the link to our Dropbox file in the description to the video. And you still have a little bit of time if you want to print that out really quick and use that as we go through some housekeeping items. But I am Mr. Tony Record. I'm a calculus teacher at Avon High School, one of the calculus teachers. I'd like to give a shout out to my colleague, Mr. Kyle Meunier, who's been working alongside me for the last 3 years. He does an excellent job with our AB students. So Kyle, thanks for all your help. You'll notice my background is a little different. I live in a state like maybe some of you live in, where our governor just declared yesterday that we will not be going back to school for the 2019-2020 school year, and it is a little disappointing. You know, you've got, it's very likely that you have a lot of passionate teachers in your life, and I know that for the teachers that live in those states, that's pretty tough. We are now the 11th state to make that decision, and it's likely that we may not be the last state. And so if you are in that situation, we definitely feel for you, or if you eventually will find yourself in that situation. And I speak for Brian. I know that when we say that, our heart really goes out to those of you who are 12th graders, because we know that this is a little bit rougher on you. But trust in the system, trust in your school corporation, trust in your leaders, because there's a lot of creative people, and I think we can put our heads together and try to create some very creative solutions to things like graduation and certain ceremonies and so forth. So all is not lost. All is not lost. And you're going to understand that probably a little bit more thoroughly when we get to the end of the lesson today, because I'm going to talk to you about a story about how people can rise in the face of adversity. So this is my classroom, right? I'm actually in my living room, but it's my virtual classroom that I'm going to use today. And this is where I teach every day at Avon High School. It's just that I won't be back there teaching students for probably a few months, but we're okay with that. All right, so our agenda for the day and the week ahead, as I said, today we're going to talk about geometric series today. It is a starred content, so that means that it is slated to appear on the 2020 AP exam. And then moving ahead to next week, Brian's going to lead us off with radius and intervals of convergence. He's going to introduce the idea of the power series to you. And then we'll kind of progress to our last convergence test that you'll need to know, the ratio test, and then talk all about Taylor approximations and then the error bound at the end of the week. And then, boy, we start really hitting the ground and running with our AP Calculus BC exam review prep, which is going to take place beginning April 13th and running for 3 weeks. Now, because I'm a little melancholy about school being closed, we have some bonus content today, right? So you are going to be among some of the first people in the country, first students, I should say, to learn a little bit more about your AP Calculus exam. The information was shared with all advanced placement teachers last night. And the official proclamation, the official documentation is going to be available later this afternoon, but we have been given permission to talk to you a little bit about that. So I'm going to lead off with that here in a moment. And then at the end of the broadcast today, we're going to take a field trip, right? I forgot to tell you about that. Did you guys get your permission slips? Everybody got their permission slips? Yeah, you in the front row, did you get yours? All right, thanks. Yeah, all right. So we're all set. We got our permission slips. So we're going to take a real quick field trip at the end of the day to Grantham, England. So what are we talking about this year's AP Calculus BC exam? Now, if you want to take a photo of this, I suppose you could. This information is going to be out. I'm not going to spend a lot of time talking about it because Brian and I are going to go over these in a lot more detail when the time comes. But your Calculus BC exam is set to be administered Tuesday, May 12th. So that's a week later than it normally would have been. And it would be at 2 o'clock Eastern time. There is a makeup date that would be Monday, June 1st. You're highly, highly, highly encouraged to go ahead and take the first one. We'll talk later about how you know you're taking the first one. You know what kind of protocol that you would need to follow. We'll take care of that later on. But we highly encourage you to be ready to take that one on May 12th in case there's some technical glitch, an issue, internet goes out, power goes out, so that you have that backup date for June 1st. The two tests would be obviously a little different. The questions would be different, of course. The test will consist of 2 free response problems. I think you have already been aware of that. The first one is said to carry a weight of 60%, and you would have 25 minutes to sort of download that problem, read through it, solve it, and then there's a 5-minute upload time that you would have to get your solutions, sent back to College Board so that you can open up the second question. And you would not be able to go back to the first question once you finish it. And the second question would be about 40% of your grade. You would have 15 minutes to solve it with another 5-minute upload time. Now, what do we mean by upload time? Well, students can take this exam either by entering solutions via a keyboard, right, on your computer, or if you want to have a mobile device, you can use a touch screen, I suppose. The other option is you could actually do your work on a separate sheet of paper, just the old-fashioned way, pencil and paper, and you could take a photograph of that with your phone or other kind of device. But at that point, you would have to send that particular image to your computer so that you could then upload it, right? Or I suppose if you're actually taking the test on that mobile device, you could just attach that picture to the interface that's there to have that uploaded. So a lot of this is kind of in the preliminary stages, and like I said, Brian and I will talk a lot more about this, but it's just gives you an idea. You can start thinking about what strategy you want. What device are you going to use? Start thinking about that right now. Are you the type that will be comfortable with keyboard input, or would you rather do the pencil and paper and attach the photograph input? If you are a keyboard input type of person, I know you might be thinking keyboard input math, how's that going to work? It seems like it would be very easy to do for AP Lang or AP Lit or what have you. But in calculus, you've got your symbols and so forth, just like you would say in a physics course. Well, the College Board is going to issue sort of a keyboard input tip sheet, weeks before the exam. So you'll have that to kind of look at. And I'm sure that's something that Brian and I will go over very, very thoroughly too in our review. So here's your preliminary information. A lot more details are going to be coming later, but at least you know the date, and at least you know a little bit about the protocol. All right, so hopefully that helps you a little bit. All right, our warm-up. It's another doozy. Thank you for that, Mr. Passwater. We had a wonderful question here. And I tell you what I like about this problem is that Brian did such a great job of writing a question that merges the 3 topics that we talked about Tuesday, Wednesday, Thursday, all into this one wonderful FRQ. It's certainly a challenging FRQ. And if you wanted to really follow it to the letter of the law and really show tremendous notation, it's a little intimidating. And our wonderful partner, Ted Gott, did a fantastic job of detailing all of the minutia that really would be required if this were to be solved, in the world of academia and done so in such a way that it was communicated effectively. So let's take a look at this. We have an alphabet soup, sort of, so to speak, of terms: A sub n, B sub n, and C sub n. And we know that K is a constant that's either 1 or larger. And our part A says, let's consider this alternating series where A sub n is on top of C sub n, and K is equal to 2. We want to know whether this series absolutely converge, conditionally converge, or will it diverge? So I'm just going to slide along with Ted's wonderful documentation here. And again, these are available, or soon will be available, I should say, on the Dropbox site for today's particular lesson. So if you go ahead and take a look at this alternating series, we just assemble it by putting the A sub n term on top and the C sub n term on the bottom. and we start thinking about, okay, we got to figure out how this is going to work. We want to look at the absolute value of this nth term expression initially so that we can make some kind of determination about its behavior. And once we do that, the alternating component essentially disappears. Now, I may have to do a little hand waving here because this n minus 5 is really causing us a lot of problems with this question, because when n starts with 1, you can see how we're going to have some negative terms for a while, right? So that's something that we have to consider. It might be more appropriate. Maybe if I started this with n equals 6 here, it could be a little bit more, I don't know, possibly notationally accurate, but we're going to go ahead and leave it like that. And we're going to go ahead and say that, all right, what does this particular series do? Is there a test that we can use to determine its behavior? And from the lesson just yesterday, Brian showed us that there's this wonderful thing called the limit comparison test. If we look at this guy closely, we can see that it somewhat resembles 1 over n, right? If we just kind of block out the terms that really don't mean much and then reduce. So that 1 over n then can be divided into that original summation or that original nth term expression. So I take my original expression divided by what I'm comparing it to, 1 over n, and I would take its limit as n approaches infinity. And once I multiply by the reciprocal and look at the fact that I have a degree of 2 for my n in the numerator and a highest degree of 2 for my n in the denominator, we can just divide the coefficients, and of course we get 1. And that's a good thing, because if you recall, we want something that's nice and finite here in this result, finite positive. So we have this one value that we can then construe. That is going to be opening the door for us to potentially have the same behavior. Well, what is that same behavior? Well, 1 over n we knew diverges. So because we have this this finite value for this particular limit expression through the limit comparison test, we know that we have to do the same thing, and therefore we diverge. So what does that mean? We've lost any chance of being absolutely convergent. That's all it means. We still could be conditionally convergent. So to check on that, we use the alternating series test. And this is where things get kind of interesting with this problem, because as you can see, this thing is kind of a hot mess for a while, right? By the time we plug 1, 2, 3, 4 in for n, we have this nice alternating behavior. But boy, when we plug n equal 5 in, then we get 0. So we kind of lose that nice alternating behavior with our signs. And what that's going to allow me to do is kind of think about starting this series at 6, right? Kind of like I indicated before. I know that the first 5 terms are going to add up to C, and that's what our solution guide here says. C is the sum of the first 5 terms. So we know that that part is nicely behaved and convergent. I'm now interested in seeing what happens from 6 to infinity. So we take a look at this and we apply the 2 criteria from our alternating series test. Criteria number 1, once again, we take the limit of the non-alternating component. That would be this expression here, and that limit does produce a 0. Check, right? That's a desirable outcome that we wanted. And then the next piece is that you observe the behavior of the a sub n plus 1 term in comparison to the a sub n. Remember, we want the a sub n plus 1 term to be less than the term that comes before it, which kind of says that this series is engaging in some of this non-increasing behavior, or we could say in this case, it's going to decrease, as you're going to find out. So if we apply a function to this particular series, we're going to call this temporarily f of n. We know that this f of n is going to decrease at some moment. Why do we know that? Well, because we cheated, right? We took a calculator and we took the derivative of this function and it graphed it, right? So the graph of f prime of n over here to the side, just a small snippet of it shows that this function f prime is going to lie below the x-axis by the time we get to around 12, actually just a little bit before 12 if you kind of squint on that a little bit. So what that means is from 12 on, we have this decreasing behavior that is abiding by that criteria that's set forth by the alternating series test. So if I let k now be the sum of the first 11 terms, right, which we know is going to be some finite sum, right? Convergent. I can set that aside and then say, now this alternating series starting with 12 is going to have to converge because I met the two criteria. Wow, conditionally convergent. It's a tough problem. It's a good problem, but that n-5, I think, is what really caused a lot of the headaches here. Okay, now, luckily, the last three parts aren't nearly as bad, but I'm going to still go ahead and just highlight them here through Mr. Gott's wonderful solutions here. It says, consider the series here 1 over b sub n, where n starts at 4. Does this series converge or diverge? Well, we go ahead and assemble it by replacing the b sub n with what he is equivalent to. And then we look at this and say, hey, we probably could use one of our comparison tests here. It seems like the direct comparison test would be a fairly easy one, because if we compare this to 1 over the square root of n, right? Because that's what this expression kind of looks like a little bit. 1 over the square root of n is divergent, right? Is a divergent p series. And more importantly, this 1 over the square root of n is smaller than the original 1 over square root of n minus 3. Remember, when you have larger denominators, let me say that one more time. If you have a smaller denominator, in the case of this n minus 3 under the square root, you're going to end up having a larger overall fraction. And because 1 over square root of n lies in that divergent zone, if you remember Brian's graph yesterday, anything that's larger than him is going to also lie in that zone. Sometimes when I teach this, I use like an airplane analogy, like the 1 over square root of n is this airplane that's flying, and the 1 over square root of n minus 3 is this airplane. Make sure my hands can be seen here. So these airplanes are flying, and we have the 1 over square root of n minus 3 that's larger. Well, to diverge, that means that the planes are going up to the sky. Right? To converge, it means the planes are going to land. They're going to come to the ground. They're going to converge to the ground. There's a finite place that the planes can get to along the ground, right? They can't go underground. But if the plane goes up to the sky is infinite. So if we think about this plane at the bottom, right, the 1 over square root of n that's going to diverge, if he's always underneath the 1 over square root of n minus 3, he's going to force him to diverge as well. So it's another way that you can kind of work an analogy to understand the direct comparison test. So in any event, we see that we have divergent behavior in this case because of the conclusion of that DCT. All right, so looking at part C, consider another series S, that's the summation starting at 5 of d sub n. And to complicate things even more, let's throw every single summation, or every single nth term expression, into this d sub n. So we have a times b all over c. In terms of k, which series should be used with the limit comparison test? Well, let's first of all assemble the series. So we have our a times our b on top and our cn expression on the bottom. We don't know what k is in this case, but if we just do a little bit of sort of mental kind of simplification here with this. If we focus on what is going to be the most important terms out of the numerator and the denominator, we can see that the numerator's degree is really going to consist of this n to the first times a square root of n, or an n to the half. That's all that really matters to us. I know you can't really multiply these two things together. You can't really FOIL those together. But if we think about what the behavior of the degree is, right, the exponent, we see that it's going to behave like a 3/2 power down the road. And down in the bottom, you can certainly see that k is going to be that power of n in this case. And we're told that k is larger than or equal to 1. So that means that k has got to be the largest exponent, at least it's a tie. And then when we look at this, n to the 3/2 over n to the k, and simplify that by dropping the n to the 3/2 to the denominator, giving it a negative exponent, we can then consolidate that exponent and call it a k minus 3/2. Now, what that means is that series is the one that we should use if we're doing the limit comparison test. And that's what the question was. What is it that you're going to compare this to? Now, because we don't know k specifically, we can't really move on any further with this. Now, in part D, we're asked to find the smallest possible integer value of k, where S from part C will converge. So in this particular case, we know that our summation of 1 over n to the k minus 3/2 is going to be a p series. Now, how do we get that? Well, we're going back to part C, if you remember. So this is our answer that we had previously. And in order for that to be a P series, and in order for it to converge, we need this K minus 3 halves being greater than 1. So we just simply add 3 halves over to the 1, and we get K is greater than 5 over 2. Now you have to be careful because we didn't really answer the question yet. It wants to know what is the smallest possible integer value. So you have to think, okay, well, what's the next integer that's larger than 5 over 2, 2.5 in this case, and that would give us the 3. All right. So let's go ahead and move on to our lesson overview for today. What we're going to do is introduce another very common series, the geometric series, and we're going to determine the conditions by which these series will converge or diverge. And then we're going to do something very interesting, something that we haven't been able to do here lately, and that is to discuss how the convergent geometric series can reveal the sum. We can actually add up an infinite geometric series and get an exact answer every time. Can't do that with too many other series. What you need to know, obviously, a solid understanding of the concepts of converge and diverge. Always techniques for evaluating a limit can come into play here. And we already kind of talked about how we've used the alternating series test just a little bit. So, we could have some application or some problems, conceptual problems that tie in some other ideas, and that's always a good piece of information to know. Another interesting problem here, what you'd be able to do, you're welcome to solve this on your own, but it's kind of working with the famous fractal, Kacha's snowflake, which consists of infinitely many equilateral triangles. For each triangle besides the one in the center, the area is always 1/9 of the area of the next largest triangle in the fractal. So if the center triangle right here had an area of 1, what would be the area within the entire snowflake? The snowflake that continually morphs itself and adds more triangles around the edges. You can actually do that. It actually has a solution. All right. Now, if we start with our guided practice, I'm going to take you guys back to Monday. Do you guys remember Monday? Do you remember the lesson over 10.1? I think I was cutting up pizzas and cake, and now I'm hungry again. So if we recall our previous lesson about when we were cutting up a pizza, recall that the pizza was cut into 4 equal slices. And I wanted to share those with Alicia, Ben, and Carlos. And then that leftover slice was then further subdivided into fourths again. And then each student would continually receive one of those new smaller slices while the leftover slices were continually subdivided over and over and over again. And we asked, how much of the pizza does each student end up receiving? And it was very easy to tell that when all was said and done, that every student was going to end up with a third of the pizza, right? Even when I take this last little morsel of a leftover piece and continually to subdivide it, it's going to seemingly look like it's disappearing because the pieces get smaller and smaller. But what we noticed was that each person was initially receiving 1/4 of the total pizza. And then the next slice that was laid on top was 1/16, and then 1/64. Well, what we notice here is that there's a common ratio, right? What is it that you would do to 1/4 to get to the 1/16? And that is simply multiply by a quarter. And you can see how that's very consistent. All right, that's extremely important. We have to have that consistent ratio. Otherwise, we do not have a geometric series. All right. Now, we knew that the sum of this was going to be 1/3, right? Just by common intuition. But here in a little bit, I'm going to talk to you and introduce a formula that you may have already seen possibly in a pre-calculus class that will allow you to determine how we can get this 1/3 without having this visual representation. Okay. So we'll get back to that in just a moment. But for now, here is our formal convergence criteria of your new geometric series. And the geometric series may have the look summation a times r to the n, where n starts at 0. I don't want to mislead you and make you think that you always have to have your geometric series starting with an index of 0. That's not true. I've looked on my shelf. I have 12 calculus books on my shelf, and 10 of them show this formula. The other ones show a formula that's slightly different. They start with n equal 1, at which case if this n was made to be bigger, then that r would just be ratcheted down just a notch. So it's very likely that in your textbook or in the notes that you have from your teacher, maybe this is the formal presentation of a geometric series. It doesn't matter, right? We could start at n equal 5, and we can still construe convergence and divergence by using this same technique. So basically, if you look at that common ratio, which is called R appropriately, if the absolute value of that is less than 1, and that's strictly less than 1, then we have a convergent series. Now, on the other hand, if the absolute value of that R is equal to 1 or larger, then we are going to diverge. So it's a really quick, what sometimes we call an eyeball test kind of test, because you can just immediately look at that R and make the determination. But you're going to have to be careful, because sometimes you're going to have to simplify things to get that R in the form that you want. So let's take a look at our first example in our guided practice here. For each of the following geometric series, find the value of R and determine if the series converges or diverges. So in this first one, we have our summation n does start at 0, moves up to infinity. We have a 4 constant out in front. That's not going to have anything to do with the convergence, right? It's can factor out to the front. And we have a 2/3 as our R. So we want to notice this as the R value. Okay. Now, I wouldn't worry a whole lot about this n-1 in terms of figuring out convergence. That n-1, it could be a little problematic if we were actually finding the sum of this, and we're going to talk about that in a little bit. But if you've got this form here and you are very confident that your R value is 2/3, you can then look at that and say, okay, the absolute value of that R is 2/3. We know that that is less than 1. And then you can make the determination that this series is going to converge. It's that easy. All right. Taking a look at part B. Now, part B has got a little bit more going on. So we might want to kind of doctor this up. We might want to simplify this just a little bit. So I'm going to rewrite this summation where n starts at 0 and goes to infinity. And then what I'm going to do is, especially in that denominator, that e to the n+1 bothers me just a little bit. So I'm going to bust it apart. I'm going to use some properties of exponents that will allow me to call this e to the n multiplied by e to the 1. We saw Brian do this earlier in the week. You're basically working backwards with your property of exponents. Whenever you multiply like bases, you can add the exponents. We're just working in reverse. Now, why is this important? Well, the pieces of this, and I'll highlight them here, the pieces of this that don't have an n exponent attached to them are really not going to have a big role in determining our convergence. They're just going to be a constant. So I could rewrite this one more time, right? I could rewrite this where I extract the 3/e in front. So it's sort of playing the same role that the 4 played in part A. And then the 2/n, the 2 raised to the n over the e to the n could very cleverly be written as 2 divided by e, all raised to the n power. Now I've got a very recognizable R value in this problem, where the R is equal to 2/e. And because it's positive, I don't have to worry so much. The absolute values is not going to change that. Now, it will be very important here to understand that e in this case is certainly a number, right? We don't like to use e as a variable when we get to higher level mathematics. And it's very important that you have a rudimentary understanding about e is approximately 2.71-ish, okay? Just like pi is about 3.14. Those kinds of things are very helpful to know when you're dealing with not just geometric series, but a lot of times power series use e and pi to sort of disguise the placement of what you would normally see as nice numbers. So if you know that e is 2.7, 2/2.7 is definitely less than 1, right? So we have another convergent series on our hands here, guys. All right. Let's take a look at part C. Now in part C, it's pretty clear that you have an alternating series. And it's easy to think, oh, now I have to use the alternating series test with this. Well, you could certainly try to use the alternating series test. And I would like you to maybe use some time to kind of investigate that on your own. It is a lot easier if you think about this as a geometric series, however, because if we rewrite this, kind of like we've been talking about before, that 3 in the denominator is not being affected by any exponent of n. So we could just bring a 1/3 sort of in front of our expression as such. And now we have this A value as depicted in our formula, right? And then the R to the N is right there. So we know that the R is -1, right? Well, we know that the absolute value of that needs to be strictly less than 1 in order to converge. Well, if we take the absolute value of that R, that's obviously +1, and that meets the criteria of being greater than or equal to 1, which is our second criteria, or our second keynote here in our convergence test, and that says that we would have to diverge. Okay. There are several other problems here in this guided practice. I'm going to leave D for you to take a look at. And if you have your document, you'll notice that there's an E, F, G, H, and we're not done yet, an I, J, and a K that follows. Now, I would like to talk just a little bit about I in this case. I, J, and K are a little different in that the series is kind of presented in a more open form. We don't have that summation notation expression. And a lot of students think, oh, well, does that mean I have to rewrite this so that it is in a summation form? Well, it depends on what the question is asking. If we are only concerned about finding the value of R and determining convergence or divergence, we could do that fairly easily without having to rewrite it. So in this case, if you think about, well, what is it that needs to be done to take a 4 to become a -2? What kind of factor, what kind of multiplication do you have to invoke here? And if you think about that for a little bit, it's, well, we're definitely making it smaller, so we're probably multiplying it by a fraction. And for it to get to 2 is taking half of it, right? And the R value is certainly going to have to be a negative number in order to invoke that sign change. So it looks like our R would be -1/2 here, right? And you want to make sure that that continues, and it does, right? If we continually multiply by -1/2, we'll get from one term to the next. And then the absolute value of that R, of course, is +1/2, which in this case is certainly less than 1. So we have a convergent series on our hands here. And you'll really do part J and K in a very similar fashion. All right. Now let's get to the good stuff. This is the really neat stuff. We talked about how you can actually add the terms of an infinite geometric series. And it's likely, depending on the state that you're in, depending on the curriculum that your school uses in pre-calculus, you may have been exposed to this just a little bit. So that's great that you can tie in those ideas from an older course. But it says if you've got a absolute value of R that's less than 1, and therefore a convergent geometric series, the sum of that series can be written as taking the A value and dividing it by 1 minus R. Now, I want to make sure that we define very clearly what is this A value, because that's where a lot of the deception lies. I know that in this form, you're saying A right there in front and saying, oh, well, there's my A value. I'm going to use that no matter what. But you've got to be very careful, especially if this N starts with something besides 0, especially if this R to the N might be written a little bit differently. You want to make sure that you just don't willy-nilly think of A as being what's present in the summation. You want to think of A as just being the first term of the geometric series, and you're always going to be able to figure that out by plugging in your very first index, right? In this case, it would be 0 for that problem, all right? R is still going to be that common ratio, but I advise you again that you're going to want to simplify like we did in the previous problems. Okay. Now, if you allow me just really quickly to go back to the pizza question. So I'm just going to go back a slide or so here. And remember that we knew that the sum was going to be 1/3. Well, we know that to be true because the sum of this convergent geometric series is the first term, 1/4, all divided by 1 minus the ratio, which coincidentally is 1/4 as well. And if we simplify this, just using some very basic arithmetic, 1/4 over 3/4 is, I know you guys know this at this point, the 4s are going to end up canceling out, and there's your 1/3 that you can get using the formula. All right, so let's take a look at some problems that deal with finding the sum of an infinite series. So this would be example 2 in your guided practice section. So we've got determine if the following geometric series converge or diverge, and if the series converges, find the sum. Well, I guess we don't really know if we have convergence or divergence, so we ought to take care of that first. So you're going to tackle this problem kind of like we did in example 1 first. So we could rewrite this a bit. Let's see, we have a 2 that sort of acts as a constant, doesn't have an exponent n attached to it. So maybe I bring it to the front like that. And then I have a 1 over 4 to the n that we could cleverly write as 1/4 all raised to the n. Right, now we can get by with that because the numerator is 1 and 1 to the n is still going to be 1 no matter what. All right, now I think we've got a good form. We also have a convergent series, right? R is certainly equal to 1/4, which is absolute value 1/4 less than 1. So we know that we converge, and it's only because we converge that we can actually find the sum. Now, the sum here could be done in a very quick manner in that you can use the 2 as your A and the 1/4 as your R. But just to verify, if you were to let n equal 0, let's say we go back even to this term. If n were 0, 2 over 4 to the 0 is 2 over 1, which is 2, and that reinforces the fact that our first term is definitely going to be 2. Our A value is 2. And then we divide that by 1 minus 1/4, and we get 2 over 3/4. And I think if you multiply by the reciprocal, we're going to find that we get 8/3. So there you have it. If we take 2 over 4 plus 2 over 4, let's start with n equals 0. If we take 2 over 1 plus 2 over 4 to the first, plus 2 over 4 to the second, plus 2 over 4 to the third, and we keep doing that forever, we will converge upon this finite sum of 8/3. Let's take a look at part B. Really like part B. Part B's got a lot of crazy things going on with the pi and the e. Once again, I think you're going to want to simplify this just a little bit. It doesn't quite have that form that we want. So what we'll do is we'll rewrite. Notice how this series starts with a lower index of 2. Right? There's a reason for that. Pi to the n stays in the numerator. And for this denominator, I'm going to call this e to the 2n. And then since I have a -4 there, what I could do is think about this as a division problem, right? I could divide that denominator e to the 2n by an e to the 4. Okay, again, I'm just using that subtraction of exponents rule in reverse. When you divide like bases, you subtract exponents. Now, if I multiply by the reciprocal here, what is going to happen is that I'm going to see an e to the 4th appear, say, maybe out in front of my expression. And then I have a pi to the n over e to the 2n, and this is where we got to be very careful. My goal would be to write this expression with a single power of n. What do I do about this 2 times n? Well, again, I'm just thinking about another rule for exponents, and that is whenever you have a power raised to another power, you would multiply those, right? That's how I got that 2 times n. Again, I'm just working that in reverse. So now I can see that my R value is pi over e squared. And that makes you think about all sorts of things here. Pi over e squared. Well, pi is 3.14. We talked about that. E is 2.71. Now, if we square E, 2.71, we actually get a number that's pretty close to 10. In fact, I think I talked about that a few videos ago. So we end up with a larger denominator, I guess I should say, than we do a numerator. So we could say that this R, which is pi over E squared, is indeed less than 1. Therefore, we converge. And unfortunately, I've used up all my space, so I'm gonna have to work down here a little bit. I apologize for that. So for the sum, I just need to find out, well, what is the first term? I wouldn't leave it to chance. I wouldn't just assume that e to the 4th is your A. It very well might be. I think it is. But let's plug 2 in just to make sure. And I might just do that at the very beginning, right? And I end up with e to the 4 minus 4 on the bottom. That's e to the 0, which is 1, right? Well, wait a minute, wait a minute. No, let's think about this. If I use this very first expression, I'm not going to get the same a sub n because this first expression was not simplified. I don't want to use him. What I want to do is I want to use this guy right here. I want to use the most simplified version of my series to extract my information. All right. So if we take a look at him and we let n be 2, what we end up finding out is that our first term would be, if n is going to be 2, did I double check in here? Let me write what I've got for my solution and see if this is correct here. If I let n be 2, my first term is going to be, have to work this out to the right here, e to the 4th times pi squared over e to the 4th. Those cancel and I get pi squared. So my first term is going to be pi squared. Okay, and then in the denominator I have 1 minus, and then my r value is pi over e squared in that regard. And you know what I think I'm going to do is probably leave it like that. You could multiply through by an e squared if you wanted to clean this up. I don't know if it cleans it up all that much because it is still pretty nasty, but if I multiply through by an e squared, I could write the final answer like that. All right. Apologize for that. I had to hesitate here a little bit because this a value, this first term, certainly wasn't going to be this guy, and it really was very necessary for us to use n equal 2 in this particular expression. Now, if we would have used this, now if I go back to this, I might need to kind of clean this up a little bit. I believe that we could have used this as well. All right, my original key had a slightly different answer and I got kind of scared there for a second. So if we would have used n equal 2 at this point, pi squared would have been our a value. So, all right. Let's take a look at C and D are a couple of problems that I'd like you guys to try on your own, if you wouldn't mind, as are E, F, and G. I think those are very similar problems that just kind of build on some of these concepts. And then let's talk just really, really quickly here about A in part 3. I'm not going to solve it for you, but I'd like to get it started. It's just to find a geometric series whose sum is represented by this repeating decimal. Well, what you're going to do here is we're going to call this 0.54 repeating 0.54 plus another value that would put a couple of zeros as placeholders for that additional, an initial 5 and 4, and then we'll plop another 5 and 4 down after that. And then if we continue to do this, and it's likely that you may have seen these in a pre-calculus class, we could do this forever and ever and ever, and that will produce this repeating decimal 0.54 repeating. Now I want you to look at this and determine whether or not this is a geometric series. And it turns out that it is. And I would like to even push the boundaries of the directions and have you guys go ahead and solve this. I think that would be great. Go ahead and see what is the fractional value that this series would add up to. And you'll notice that in the key, we present the problem just like that. So A and B are really good problems here in example 3 to kind of tie this into really a basic type of number theory question. All right. The check for understanding consists of 2 wonderful practice problems that we are going to assign for homework. They're wonderful questions that start to invoke the idea of a power series to a degree, but you are, in this particular case, you have this unknown value of k. And in part A, we ask that you find that value of k such that the summation is equivalent to 3. In part B, we ask you to find that value of k so that the summation is equivalent to 4/3. And then in part C, we say, well, there is no k, so that this summation is going to equal to 1, but you have to explain why. You have to show why. So it uses the same idea of the sum of an infinite geometric series, S being the first term over 1 minus R, but just in a slightly different environment that forces you to find that value of K. And there's two different versions of this. So if you have a little bit of trouble with practice 1, you can check the key. Don't look at practice 2's solutions, but then learn from your mistakes and then try this practice 2 and then check the answers on the key to see if you did a little bit better. Debrief and summary for today. Well, what did we do? Well, we applied our enduring understanding again that limits will always allow us to determine the finite sum of infinitely many terms. That's an overriding theme here this week. Our key takeaways is that a geometric series is a series with a constant ratio between its successive terms, and that the standard way of maybe presenting one of these, the summation of a times r to the n, where n starts at 0 and goes to infinity, will converge if the absolute value of that r is less than 1. And then we know that the sum of this convergent geometric series can be written as a over 1 minus r, where a is the first term, r is the common ratio. There are lots of misconceptions and errors that students can make. Two of the most common ones, be sure to simplify or rewrite those exponential expressions before determining what your R value is and whether or not your series converges. You saw that happen quite a bit in our examples. And the use of the formula for the sum of a convergent infinite geometric series does not require that lower index to be 0. Just be sure that the value of A is the first term. And another one that I didn't write in here, but you have to be very careful, because if you have a divergent geometric series, nothing is going to stop you from trying to use that formula, A over 1 minus R. It will produce an answer. It will be a wrong answer. So you have to know to not use that summation formula, A over 1 minus R, unless your ratio is less than 1, or the absolute value of your ratio is less than 1. All right, the AP exam practice problem is another fantastic one, a 3-part problem here that does a great job of leading into Brian's discussion on power series and the interval of convergence on Monday. But you're going to be given this particular series with this unknown K, and you're going to be able to find the value of this series when K is 1, find the value of K if that series is equal to 12, and knowing that that series converges when K lies between A and B, you're going to be able to find out what the A and the B values are. So it's a wonderful problem to lead into that. I promised you we're going to have a real quick field trip here. So in lieu of our Twitter shout outs, I want to kind of share an experience that I had a few years ago. I was very blessed in the summer of 2016 to travel to Europe to investigate the birth of calculus. I had been so enthralled by the story of Newton and Leibniz that I'd spent 3 years researching it heavily. I read 7 different biographies of both of those particular mathematicians, and wrote up a proposal, and I was very fortunate to be able to win and go and take my family with me. And the trip began, in London, which is the hotbed for where Newton spent most of his adult life. But what I wanted to do is just take you on this little field trip here up to Woolsthorpe Manor. Now, to set the stage here, young Isaac Newton was in his 2nd year in Cambridge, and Cambridge, obviously, very popular institution of higher learning in England, still in service today. And he was holed up there at Trinity College there in Cambridge. And at the time, Europe was under the siege of a plague outbreak, and it wasn't the first time. It's kind of ironic that we're kind of not dealing with so much a plague, but this COVID-19 is certainly on our minds. But back then, it was a common occurrence. Europe didn't mess around anymore, right? When they went through the big plague, the Black Death, which basically led to the Dark Ages, they wanted to make sure that they were prepared, and so they were very good at exercising social distancing, right? So basically, all of England closed down, Cambridge shut down, everybody had to go home. And so young Isaac Newton, at around age 21, found himself going back to his boyhood home of Woolsthorpe Manor, which was just, about a 3-hour carriage ride, horse ride north of Cambridge. Now, while at Woolsthorpe, a lot of really amazing things happened. And that's what we're going to talk about here. But I'd like to give you some pictures. And right here is the exterior shot of the home that Isaac Newton was born in. And this house was built, about a century and a half before Newton was born. This is in the late 1600s. 1665 is the time that Newton left Cambridge to go back to his home. And it was on a farm that was pretty much renowned for herding sheep. Um, at a young age, Newton, when he was born, his father had passed away prior to his birth, and his mother had raised him for a few years, but then his mother met someone else, ended up marrying a local pastor, and ended up being basically the stepmother to his children because he had lost his wife previously. And I know that sounds terrible for his mom to leave him and live in another home, but it wasn't really all that uncommon at that point. And young Isaac went ahead and stayed at this home, and he was essentially raised by his grandmother during that time. Well, anyhow, as an adult, Isaac would retreat back to this home, and I'm going to give you a little bit better view here of the front entrance. And one of the things that people are going to always note here is, wow, look at those. What the heck? Is that like somebody graffiti? Is that, spray paint? And what that is looks like an integration symbol, of course, but those symbols were a part of that home long before Newton was born. Those symbols are basically iron beams that sort of reinforce that second level. And the big irony to this is that that symbol is not even a symbol that was instituted by Isaac Newton in the first place. It was definitely one of his sort of I don't want to use the word enemies, but one of the other founders of calculus. But it's very, very serendipitous that that symbol is used and it appeared on Isaac's home his whole life. Right up here, it's the room where it happened. And we're going to take a little bit closer look at that room here. Here's the interior of that room looking out that same window. Yes, that is an apple tree, right? Is it the apple tree? Well, there are lots of stories about the apple tree being in Cambridge, lots of stories about this apple tree. Agronomists have basically determined that the bark on this tree, the tree itself, is a descendant of a tree that certainly lived there 350 years ago. But in this room is, for the most part, where a lot of the foundations of the calculus that we study was first discovered by Isaac Newton. Here's a table right by that window that has an array of papers. Those obviously aren't original manuscripts, they're reproductions. The desk is a reproduction as well. They feel like from a lot of the information that they gathered, this was very similar to the desk that Isaac Newton would have written upon. Those particular papers actually list his sins. Isaac Newton was a very religious man, and he would write his sins down every week. So I can just imagine him sitting at this table during the outbreak of this plague, kind of developing some ideas that led to his fluxions, which are what we call derivatives now, possibly looking out that very same window. All right, and kind of close this out. This is the tomb of Isaac Newton after, of course, he died in Westminster Abbey. This is probably a little scary to show this because I'm not really supposed to take pictures in Westminster Abbey, so shh. But we see to the left, it's a wonderful monument that's devoted to him. It's probably one of the most ornate monuments in all of Westminster Abbey. And then to the right is sort of the slab along the floor where about 8 feet under that rests the remains of Isaac Newton. And we can see that this is written in Latin, which was the common way to depict, tombs of dignitaries at the time. This bag here, what this bag is basically, I always give my students at the beginning of the year, as soon as they answer their first question, a little band that has the name of our school colors with AP Calculus written on it. And I always take I took a whole batch of them with me, several hundred of them. And I actually took them into Isaac Newton's chamber. I got permission to rub them on his walls. I was a little scared that I was going to have a restraining order on me. And I actually took him to his tomb as well. And a lot of teachers around the country that I do workshops for like this idea. And I tell them, if you buy your own bands and send me an email, I will send you one of the bands that has Avon High School on it with Newton's aura, and you can mix it with your bands you distribute to your students. And then we have the Newton of aura going around. Now, we might want to hold off on that right now under the current circumstances, but later on when things settle down, that's certainly something that we can try. Little known fact about Newton before we close out. Isaac Newton spent the last part of his life as the head of the Royal Mint. And there was a big problem in Europe with people clipping coins. Clipping a coin is basically taking a knife and shaving off the outside edges. And coins at that time were precious metals. That's how they had value, silver, gold. And people would sliver off just a little bit of silver on the coin, put it in a drawer, and the coin would still have the same value. But this posed a big problem because as that silver slivers stockpile kind of grew, they could cash that in. And with enough people doing this, it can really flood the economy with money and causes inflation. It's a big issue. And so Newton wanted to put an end to that. And he was actually sort of part of a team that made a decree that people could be executed for clipping coins. And it's because of his work there with the Royal Mint that if you take a quarter out of your pocket and you look around the outside, it has those ridges. And those ridges are there so that we can tell that people didn't clip the coins. So he had a lot of really interesting impacts into the world of economy in that regard. So anyway, I hope this was a little bit of a nice excursion for you. I always enjoy sharing this with people. It's one of the criteria of having received the grant that I always try to share this knowledge with students. And it's great to kind of understand a little bit of the history of how calculus developed. It's really a soap opera when you look at what happened between Leibniz and Newton. And I certainly would encourage you guys to read up on that. Once again, we always want to make sure that there's proper access. So if you have having trouble, or if you have a friend that's having trouble getting online, especially before the AP exam is coming up, make sure that you reach out to the College Board at cb.org/tech, and they can get you certainly squared away. Certainly enjoyed today. I want you all to have a great weekend. You deserve it. And we're going to come back Monday with a great lesson from Brian. So we'll see you then. And in the meantime, we definitely want you to stay safe, stay healthy, and keep learning.